Welcome to the solution video for question 2 of the modules of Moore's circle of 3D stress and static failure theory. In this question, the stress at a point is shown on the element. Determine the given principal stresses and absolute maximum shear stress. So the first thing we want to do, we want to note out what our given details are. From our element, we see that we have shear stress in the XZ direction as 1 megapascal. We have a normal stress in X as negative 1 megapascals. We also have a negative stress in the Z direction as negative 6 megapascal. Our normal stress in Y does not exist, so it's just 0 megapascals. There's a reason I've noted that out. So recall from question number 1, we want to check for principal stresses. So principal stress exists when there are no shear stresses on the axis, on the plane for our normal stress. So we're going to do a quick method of this. So check for any principal stresses. So the quick method. When we have been given a shear stress, so shear stress in the XZ, we can already from here know that we will have a principal stress in Y. So the way I would do it, I would just check, is there any axis missing from our shear stress? In this case, we don't have a Y in the shear, which means the normal stress in Y would then be a principal stress. So the more detailed way of doing this was presented in question 1. So if you're a little bit confused on how I went this quickly to find my principal stress, please go ahead and go back to question 1 for a more detailed way or method to approach this. So what we want to do now, we want to draw our element on the plane where our Y is then our principal stress. So we are then looking at our XZ plane, right? So the easiest way I would say to do this, rather than looking from this direction into the plane, I'm going to look from this direction, because that way my axis, my X axis, will point to the right hand side, just to make it a little bit easier when it comes to the shear stress direction. So draw the element, the simplified element. So it will then be in 2D. I have my Z and X direction. My element. Have my negative 6 megapascals in the Y, which means it's going into the element. And similar for our X, it's going into the element because it's negative 1 megapascals. We don't want to forget about our positive shear stress. And this is what I mean with the direction being a little bit confusing, where if we were to look at the opposite direction. One megapascal. We can now go ahead and apply this details for our Moore circle. And again, we're only interested in our radius and center, so our center being our average, which is just our normal stress in x plus z divided by 2. So -1 plus -6 divided by 2 is -3.5 megapascals. We then want to find our radius. Square root our normal stress in x minus the average stress squared plus our shear stress squared. And what we will get is simply -1 minus 3.5 squared plus our shear stress, which is just 1 squared. Then my radius is just 2.69 megapascal. From this, I can draw out my Moore circle. I will draw out my center point. My principal stress 2 and my principal stress 1. I'll go ahead and calculate my principal stresses. My principal stress 1 is just my center plus the radius. So if I look up here, I will have -3.5 plus 2.69, which will give me a negative value as -0.87 megapascals. And my principal stress 2 is then my center minus the radius, -3.5 minus 2.69, and that will give me -6.2 megapascals. So I've just rounded that there, I realized. Just bear that in mind, it's been slightly rounded. All right, so I now have my two principal stresses on this circle. I can tell that my principal stress 2 is going to be my minimum principal stress. But what about my principal stress 1? Is that really my maximum? Well, if we recall, we already found our principal stress 3, we're going to call it that. I found that earlier on. So if we scroll up, it's the same as my principal stress in the y direction, and it's 0. So principal stress 3 is my principal maximum stress, which means my principal stress 1 is the same as the intersecting stress. So if we draw out our shear stress axis, probably located quite close because the distance is just 0.87, somewhere around there. Then my principal stress 3, or if we want to call it the maximum principal stress, is located on 0. If you recall from the previous question, we drew out the elements with these new principal stresses in order to find the circles. You can go that way if you want. Or we also explained you can go the quick and easy method, which means that we now know that our largest circle is going to connect between the maximum and the minimum. So I'm just going to draw out my larger circle. If we, for some reason, need to find our center points and so on, we can now do that because we know the diameter of our largest circle. But before we find our absolute maximum shear stress, let's also draw out our smaller circle. Which will be located between the intersecting stress. So I'm just going to put that in here as well. And our maximum. So again, we will always have a circle between our minimum and the intersecting circle, and the maximum. And then the larger circle will be between our minimum and maximum principal stresses. Now that we have our larger circle, we can go ahead and find our maximum absolute shear stress, which is located down here. And either we can do this graphically because we know that it's located between 0 and our minimum principal stress, 6.2. And from that, we simply know that our radius is going to be half of our principal stress 2. Or we can recall the formulas from, you might have seen them in your lecture, or if you have a textbook. If you have two values that are the same or opposite, we have different calculations or formulas to calculate our maximum absolute shear stress. In this method, we actually considered our max to be kind of, I would say it's unsigned, so it would still be considered as an opposite sign. But again, max minus min divided by 2, and in this case our maximum is then 0 minus 6.2 divided by 2, which is 3.1 megapascals. So just again, either you can just apply the formula or from the graphical interpretation in here. Sorry, that's the wrong center point. The center point should be somewhere around there, right? So from here, knowing that it's 0 going all the way there, we have the diameter, and we can find the radius that way. And that sums up this question.